everybody. I hope everyone's having a wonderful day. So we started last class talking about binary search trees. Now remember, a binary search tree is a proper binary tree. That means that every internal node has exactly 2 children, where what we're going to do is we have to make sure we maintain the so-called binary search tree property. That is where if I give you some node, all the nodes in its left subtree, which would be the left child's subtree, have key that's less than the key in my node, and all the ones in the right subtree, which is the tree rooted by my right child, is the one that has a key, and all of its keys are greater than my key in my node. So many of the algorithms we've been doing take advantage of this property. So last day I talked about how you can get the smallest and also how you can get the so-called record. But remember, I told you that we're just going to get the node itself so we can reuse some of these methods. It's worth noting that if you ever wanted to implement them for a proper order dictionary, you can actually just use these methods and then just make the small tweak. Okay, so let's talk about how you would put things or put records into our binary search tree. How would we do that? Let you think about it. I'll give you a hint. We actually wrote a method that does all the work. So what did I say last day when I talked about get? I will be able to find it by either choosing left, right, or I get a match, right? What happens when I don't find the record or node that's storing that record with that said key? It goes to a leaf, right? Why don't we use this? So let's use get. And then, when do we know? Remember, in order dictionary, we're not allowed to have duplicate keys in the dictionary, right? How do we know we hit a duplicate? If we get what? What should we get? If we get an internal node back, that means the node already exists for that record, right? So, if we get an internal node, what does that mean? There is a duplicate. Meaning we should insert it into the tree, right? Otherwise what? Otherwise, it is a leaf. Now this is where the versatility of this implementation becomes really nice. All you're going to do is you're just going to expand this leaf into a node that stores your record, and then you're going to create 2 leaves with that node. That's all you're going to do. So it's really nice. So let's talk about this. So imagine I have put, and imagine I give you the root r, because remember, in a binary search tree, the main attribute is the root, which is what you get access to. So you start off at the root, so this would be what you give it initially. So you give it the root r, and say we're going to put in 12. What did we do last time when we got 11? Remember, we went this way, then we went that way. Remember, we compared the keys, and we see which way it should go. Left if it's less, right if it's greater. So I would go down here. Okay, well, 12 is bigger than 11, so I go down here. So I went right, then I went left, then I go right, and I hit this leaf. I return this leaf when I finish my get method. So I get my get call, I get back this leaf node. What should I do to that? I should put my record into there and then create 2 leaf nodes. So let's do that. So now the right child is going to be 12, and then I create two leaf nodes right there. And that's put. It's really not that bad. So let me because we're gonna reuse this tree several times today, I'm just going to erase the arrows. Let me write down point. Let's write down the algorithm as pseudocode. Put So I'm going to take the root R. I'm going to have my key and some data. Root R, key K, data D. And I'm going to make, again, like I said, this is going to be a small modification. So return true if I do the insertion correctly, false means there's a duplicate. So, like I said, I'm just going to use get first. So I get back a reference to some node. If P is an internal node, what should I do if it's an internal node again? I should return false, right? I return false because I hit a duplicate. Because if I use this get process and I hit one of these, like if I try to put 13 in, it would give me back this node. And that's an internal node, so hence there's a duplicate, so I shouldn't do any insertion. Else, otherwise we have a leaf, right? So we're going to say that P dot key is going to be just K. P dot data is going to be D. And then I just create two leaves, and set them as children of P. Now, one thing that's worth noting is whenever you do this, remember, don't forget about parent references. Those children have parents, right? They're not orphans. Then after this, you're just going to return true. And that's it. Okay, so now this is the great thing. What's the time complexity of this? What's time complexity? How long does get take? It takes big O of the height. And how long does everything else take? This all takes constant time, right? All other operations take constant time. Probably put the word time in there. I'm getting excited here. Takes big O of 1 time. So, how long does put take? Put takes big O of the height of the tree, right? So put takes big O of the height of the tree. That analysis is a lot easier. We're piggybacking off of get. Do you see why I do that? It's so that I don't have to rewrite a whole bunch of things over again. This get is very convenient. So that's how you can put records into the binary search tree. How about if we want to remove records from the binary search tree? Now I'm going to adopt a very similar convention again. I'm just going to return the node itself. So let me think about this. Let's see. Getting ahead of myself. Here we go. So I'm going to do something very similar to put for my remove. I'm just going to say it returns true if the node with that key was removed, false otherwise. Now, there might be a variant for which you might naturally want to return the node for which the removal did happen. But here we're just going to have a nice little Boolean operation here. Now, before we get into anything too technical, how would you naturally remove something like number 3 here. How would I remove 3? Well, it seems really easy, right? I would use get, and I would find this one. I would give you back the node, and then I would perform a little bit of surgery. Maybe I'll cleave that off and say, hey, look, there you go. And I make sure that this one has two leaf children. Does everybody see that? So on nodes that are really close to the leaves, it's really easy to see what you do, right? How about here? What if it was 2? If I remove 2, you'd agree with me if I put 3 right here and just axed off anything that's down here, or just do some surgery, just shift this up, because these leaves don't store any data in, right? You can almost look at this like I kind of take this away, then I put this, I shift this and put that there. I could easily do that. How about if it's, say, 13? Or 10? What if it was 10? What would I need to do then? Does anybody see what we might need to do here? Well, if I try to remove 10, we're going to use an idea that we used before when we were talking about heaps. What did I do there? Well, remember there I was trying to find, I want to have it where I replaced it such that I don't destroy the structure of the tree, right? I'm going to do the same trick here. What would I want to naturally do? Maybe what I should do is, should I put this one there? Well, that's pretty big, right? I maybe don't want to necessarily do that. What should I put here? I want to put something here that is bigger than 7, but is less than 13 if possible. Well, probably the more convenient one maybe would be to maybe put 11 here. Maybe 11 might be a good idea. So, naturally, to do a removal, we have to hit what kind of node? An internal node. So, for an internal node, there are 2 main cases to consider. So the first case is that if P has at least one child that is a leaf. You see how that might be a useful case to consider? That looks a lot like if I was trying to remove 2 here. You see that? This has 1 child here, so I can do my little shuffle game where I just kind of put it here and then, hey, look, it works. Okay, that's an ideal case. Well, we have the other one that, like, if I try to remove 10 there, if both children of P are internal nodes. You'll notice that a lot of the difficulties come from when we have both the children being internal nodes. If it isn't an internal, if both aren't an internal node, you can see very quickly I can adapt that same strategy almost everywhere. Do you see that? So, for example, if this is 1 leaf right here, if I deleted 7, all I have to do is just kind of move that up like I did before, and we're done, right? So, we have these 2 cases we need to consider. So, if I was attempting to, say, remove 2, if I tried to remove 2 from this, so I pass it the root, I give it, let's go 2, and some data. Actually, no, sorry, I don't even need any data, right? I just need the key. So, remember, remove takes a key. Anyways, so we're just going to use that strategy I just talked about, where I'm just going to pretend this doesn't exist. I move this up, and then I make the parent of 3 7, and then we're good, right? And just make sure you assign that the left child of 7 is 3, right? So that's really easy, right? Does everybody see that? So I just put 3 here. So that's the easy case. So that's what we do when we have case number 1, right? Case 1 is really easy. How about case 2? Case 2 is a little trickier, but you'll see that it's actually really just like I'm doing 1 extra step on top of case 1 here. So if I can make sure that there's some node I'm going to remove that is going to fall into case 1, we're done. So that's going to be kind of like my big goal here. So what should I do? Well, one thing I want you to observe, this is a big observation. Notice that if I consider the leftmost node of my right child, if I assume this was the subtree, if I go left all the way, I want you to look at the leftmost node. What property does it have? Well, with far left as possible, right? We can guarantee this is the smallest key in this subtree. And look how many leaves it has. It has 1. At least 1. That's case 1. So that's a perfect candidate for what we should be doing things with. So what I'm going to do is I'm going to copy. So I'm just going to take this. I'm just going to take 10 and I'm just going to kind of cross that out. I'm going to put 11 here. So whatever data was here, I would put it up there. And then all I'm going to do is I'm going to apply a removal on this node here. So if I do the removal on this, I need to do the same trick. Candidate isn't there. I move this up, then I update the parent and the left child here. So note, for symmetric cases, you do the exact same thing, except you have the right child. So I'll just put 12 right here. So it's just 2 steps, and it's really not that bad at all. So in this case, what I do is I determine what? I determine the next largest key that is bigger than the one I'm trying to remove, which happens to be the smallest one in its right subtree, right? And then I copy its data up to the root, or wherever I'm removing it from. In this case, it was the root. I'm getting a little excited here, as you can see. I don't know how many times I've said that this term. Somebody should make a compilation of this. The point is that I copy those contents into whatever node I'm trying to remove, and then I naturally delete the one for which I did the copy from, which is quite nice. Does everybody see that? So the whole idea is that case 2 actually is really just going to be one step where I find the one just above it, which is what? It's called the successor. So that's the successor. Do you remember I talked about the successor the other day? So if you could figure out what the successor of your node is, then it's pretty easy. But the great thing here is that we really know how to find the successor, because we have 2 children. And those 2 children are what kind of nodes? They're internal nodes. So we know they have some records there. Okay, so let's write down remove. So remove, I get the root of the tree, and K, the key for which the record I want to remove. So input root R of the BST and key K. Okay, the output. So for this case, I'm just going to make it so it's true if node with key K was removed. False otherwise. So that means that an error happened, because that means that I tried to attempt to remove a record which doesn't actually exist. So remember, in our other operations we had it where we throw an error. I'm just going to make it so it returns false if that happens. So what can I do here? The first thing I should naturally do was what? I'm going to reuse what I have already. So this is going to be naturally what I'm going to do. This is where it all came together. So all I'm going to do is I'm going to apply get, given the root and the key. What should happen if I encounter a leaf? Okay, if P is a leaf, then I should return what? I should return false. Because I didn't find it. Otherwise, what? I might need more space for this, so I might need to write it down over there. Okay, otherwise, now we're going to have our two cases. I'm going to write down case 1 first, and I warn you when you're implementing something like this case, you have to be very careful. I would consider this kind of like doing surgery for the first time on a linked list when you forget how to properly reference given nodes when you perform a deletion. You're going to find that this is going to be somewhat similar to that, so make sure you carefully maybe even draw a picture of what you're making your references to if you ever try to implement this method, okay? So if P has a child, C, that is a leaf. So just as a reminder, this is case 1. So this is case number 1. So if I encounter case number 1, what should I do? Well, I need to make sure I hang on to certain things. So I'm going to call P prime is going to be the parent of P. P prime is the parent of P. Because I need to hang on to the parent of the one I found. Remember, when I removed 2, I needed to make sure I didn't lose 7 here. So P prime would be 7. Okay, C prime is just going to be the other child of P. So in my example, so if I'm trying to remove 2 here, so my get operation would find me P. So this is P. P prime is its parent. This is C. That means the other child of C is C prime, that's the 3 there. Okay, so if P is the root, because sometimes we might need to actually update what the root of the actual tree is the root, then, so if that's the case, then what you're going to do is you're going to make C prime the new root. Otherwise, the following is going to occur. Otherwise, make C prime the child of P prime. So if I'm getting rid of P, right? P's going to go away. I'm doing my little bit of surgery here. So what I do is I'm just going to almost basically say, hey, look, there's this thing here. Okay. So now the new child is going to be right here. Okay? So I'm saying make C prime the child of P prime. So now the left child, instead of it being P, is now C prime. Everybody see that? So remember, this literally matches up with what I said before. You just take this, you pretend this is there. And that's what's happening right here. That's case number 1. Let me write case number 2 over here. At first it's going to look a little strange, but I promise it's going to be very simple. I would argue that's the tricky case, although it seems rather simple. So this is going to be case number 2. So if we have 2 internal nodes as children, then I'm going to assign S, this is going to be some node, is going to be the result of smallest being applied to the right child of P. So I just apply to the right child of P. I go all the way down to the left. And then I get the node that contains the smallest record of the right subtree. And then what I'm going to do is I'm going to copy the key and data from S to P. And then what I'm going to do is what I just described. I'm just going to delete, or in our case, remove. I'm going to apply remove on S with the key in S. So I'm just going to apply this. Now, remember, as I justified for you earlier, that is just going to be case 1. So you know this is actually going to terminate when it recursively applies remove again. Else, and that's it. That's case 2. And at the very end, we're just going to return true, because we know for certain there would have been 1. We would remove it. Okay? And that's it. That's the end of remove. That's supposed to be a closed semicolon, a closed curly brace down there. Okay, so this is remove. I would argue this is the tricky one, but once you understand the idea of these two cases, it's really not too hard at all. So I want you to just keep in mind these two cases and just how we perform our little operation here. Remember, in case 1, just pretend it doesn't exist, and you just grab this one and put it there, okay? And it would also be symmetric, obviously. Second case, you just find one where you could replace its successor. And then you copy that into the appropriate node that you're removing. And then you would just perform case 1 on the node that you copied the data from, okay? That's it. So, let's talk about the analysis. Now, I'll let you look at the notes for the analysis itself, but I'll kind of walk you through it here together, because a lot of the bits and pieces we already have. Okay, so get. How long does get take? We already established this takes big O of the height. That's big O of the height. How long, so if you notice that there is some recursion technically over here in case 2. How long does case 1 take? All these are constant time operations, reassigning pointers. So all of this is going to take some constant time. What about this? This seems a little bit, be a little bit careful here. Smallest takes how long? Takes big O of the height. It takes big O of the height. That's supposed to say height, by the way. It's been a long day. Big O of the height. Copying this takes constant time. How about this? Well, okay, remove. That's applied to the successor of the node you're trying to remove, which by guaranteeing, we've always computed the smallest, we go all the way to the left, and we can guarantee that it's going to always fall into case 1. So I should point out that this is always case 1. And how long does this execution take? Well, it's big O of the height, right? Because that's called get on that node. So this takes big O of the height. And then it will just execute case 1. So how long does remove take? So remove takes big O of the height time. You should see a pattern here. All of these take big O of the height. Just really a nice property. So, let's talk about one more thing. So, I recommend, if you're really unsure about this, draw out your own binary search tree and try removing some nodes from it and see if this makes sense to you. I often find with students, this is usually one of the trickier cases here, but you need to be comfortable with this one. Okay, so that is remove. We're going to do one more operation. We're going to talk about how you compute the successor more generally. Now, I showed you how you can compute the successor in the easy case. What did we do in the easy case? Well, I knew I had 2 internal node children. So I always know the successor if I just call smallest on its right child. But that doesn't always happen, right? That doesn't always happen. So we have to be very careful. So what do we have to do? You have to be very careful. So let me draw just another tree here, just to illustrate my point. Okay, so here's a binary search tree. Okay, if I wanted to compute the successor of 3, what would I do? I would do exactly what I did in case 2, right? All I do is I find the successor of the right subtree, which is just simply calling smallest by giving it the right child, right? I just go. Then I go all the way to the left and I get 5. That would be the successor. Remember, the successor is given some key. Tell me what is the key, the smallest key that is larger than the key I give. So if I give you 3, I should get 5 here. However, not all of them will work out like that. Say instead I have 1 here. What's the successor of 1? It's 2. Well, there's nothing to the right of it, right? Where is it stored? Well, I always know that my parent has to be bigger than me. Right? At least if I'm a left child. That's the big observation. If I'm a left child, then I know my parent has to be bigger than me. So it doesn't matter if this chain keeps going all the way down to the right. If I had more nodes here, I would keep going up until I hit the parent being off of a left child, okay? So I've clearly actually identified the 2 possible cases that can happen. If I have a right child, I know I can go right away and find the successor. However, that may not necessarily happen. I might have to go work my way up the tree. So let's talk about the successor. So what we're going to do is we're going to find the next largest key, and the BST given a key K and the root R. There are 2 cases, and we've identified them. There are 2 cases. First one is the easy one. There is a right internal node child, implying the successor must be the smallest node, must be in, that should say in there, be in the smallest node of the right child. Remember, this is exactly the one we used in case 2 of remove. Case 2, node with K is in a subtree rooted by the successor. Remember, like I said, it might eventually, you have to follow up your parents until you're eventually hitting the node that is just the appropriate one. If you're going up like this, you're going to be on the left of the successor, okay? So let me write down the algorithm. So we're going to write down successor. I'm going to give you a root and some key. So input is going to be the root R and key K. Output, we're going to give back the node storing the successor. Node storing the successor of K, and null if it has, actually if it has no successor. Okay, what do we know? If I have a leaf, what should I know? If I have a leaf itself, that must mean that the tree is in fact empty, right? If R is a leaf, then return null, right? That's how we've been doing a lot of these ones. Otherwise, we're just going to use get again. It's like what we've been doing before. I just get the one with the key and then I find the successor. So if P is an internal node, and the right child of P is internal, what should I do if that's the case? If P is internal and its right child is internal, what should I do? I should then return the smallest on what? The right child of P. So I return the right child of P. Otherwise, this is, by the way, case number 1. Kind of running out of space here. This is case 1 right here. This if statement, that is case 1. Otherwise, we have case 2. So in case 2, I'm going to create a reference to a node. I'm going to call P prime. This is going to be the parent of P. So what I'm going to do is I'm just going to work my way up the tree. So while P is not equal to R, remember P is my current reference here. What I'm going to do is I'm going to work my way up. You can imagine me having P prime, where P prime is working its way up the tree, and I'm dragging P along with it. And P is the right child of P prime. Why? Why do we need to care about it being the right child? So if I keep going up, and as long as I'm the right child of that node, that means that I was bigger. I'm always going down, right? Because everything if I go down to the right, I get bigger, right? However, if I have it where, so you have to imagine like P prime's here, P's here, and I work my way up, and then there's going to be a switch that happens like this. As soon as if P is no longer a right child of P prime, then we know where is the successor. Where is the successor? It's P prime, right? So P is going to be assigned P prime, and then I'm going to say that P prime is now the parent of P. So I have this while loop. Now I have 2 cases. Either I'm going to make that P is in fact the root itself, which if it becomes that P is the root, that means that P prime must have flown off into outer space, because Remember, it's doing this process where it's kind of going up like this and we're getting dragged, but P prime is now beyond the tree, meaning that it's null, right? So if P equals R, then return null, right? Because there is no successor. And I'll write it down here, but I'm running out of space. I'm just going to put the else below over here. Else return P prime. So you're just going to return P prime. Remember, that's the parent that's pulling along P. Remember, we're looking for when that switch occurs. So, for example here, if I instead had right here, let's make this a little different. Let's say this was 4 here, and this is, say 3, and this is 2. P would be here, P prime would be here. I go up, and you see that they crisscross, they cross, right? It starts going from a right child to being a left child. You know that the successor of 2 is 3, right? That's what's happening here. But if you keep going up the tree, you're eventually going to have it where P prime is just going to be sitting up here. Does everybody see that? So, for example, if I wanted the successor of 7, what would I do? Well, P would be here, P prime would be here, and what would happen? That loop is going to say, okay, well, this is not the root yet. So what I do is I go up. So now this is going up, P prime's going to drag it, now P prime is up here, and it's like, hey, look, this is the root, it has no parent, right? So it's null, and thus now P is equal to the root, violating that first condition of the loop. And then since P is equal to R, I return null. Does everybody see that? Okay. So that's how you can compute the successor of an arbitrary key in the binary search tree. Let's do the analysis the same way, just for the sake of time, because the analysis is very similar almost every single one of these cases here. Once you see it once or twice, I don't want to waste too much of your time. I hear a train. The train is saying, hurry up, okay? So, how long does this take? This takes some constant time. Well, I'll say that this takes constant time, right? How about this? Okay, get takes how long? It takes big O of the height. Okay, how about this? How about case number 1? Case number 1, it computes the smallest, right? So this is going to take big O of the height if it occurs. So if it happens, you're going to deal with big O of the height. How about this? There's a very real possibility that I might be computing the successor. Actually, I'm missing the leaves down here. You'll notice that there's a very real possibility that if I might end up being way down here on the right side, and I might have to compute the successor, but it's like really close to the root. Either way, you can notice that it's going to have to go all the way through, at most, the height, right? Height plus 1 again. So that's going to be a nice bound here. So we know that this thing here is going to take big O of the height, at most. And all the rest of this takes constant time, right? This takes constant time. This all takes constant time. So how long does this algorithm take in the worst case? Big O of the height. So the successor takes big O of the height time. So you can compute all of the operations I've shown you here in big O of the height of the tree. So that brings me to a natural question. What is the height? So we're going to switch gears. We're going to start talking about a topic. The next topic we're going to talk about is AVL trees. But before we actually talk about these specifically, I want to talk about what we're doing here with binary search trees. So all the operations we discussed take big O of H time where H is the height of the binary search tree. Right? That was a big thing. So how bad can this be? Well, let's be optimistic and let's think about what the tree might look like. So one possibility among many is where we end up with a so-called balanced binary search tree. I'm just drawing in my leaf nodes. So this is one possibility. What is this called? This is called a balanced, this is a balanced binary search tree. So notice that any one of the leaves, they don't differ by more than one in terms of the level that they're on. Does everybody see that? So what's the height of this tree? Well, I'll tell you, I'll let you think about it if you like. It's the ceiling of log base 2 of n plus 1 minus 1. The point is that a balanced binary search tree has height that's big O of log n. So this would be an ideal scenario where our tree is what we would call height balanced. So height balanced trees have height big O of log n. However, this isn't guaranteed. It's a very real possibility that your tree, your binary search tree, upon several insertions or removals, it could degenerate like this. Or at least something that resembles this. You get a chain like this. So this is a degenerate binary search tree here. And its height is big O of n. Does everybody see that? In fact, if you want to get more exact, we can use the property that the height h is less than or equal to the number of internal nodes. Remember, this is one of the properties I brought up, but this is in fact equal to n minus 1 over 2. So in this case, you have a really nasty thing where it either could be really nice and balanced, and then it's somewhere between here and there. What we would like, and this is going to be our goal, is to maintain a binary search tree that is height balanced, meaning its height is big O of log n. So it's allowed to be some constant factor away from the balanced binary search tree. But the point is its height is big O of log n. So just as one last thing we're going to say today is that we're going to address this by asking a very simple question. Like we have in the past, can we maintain a height-balanced binary search tree? Is there a way to do that? That's going to be our goal next. So I have a very simple question for you. If I can maintain a binary search tree that has a height balance property, how long do all the operations I described to you this lecture and the previous one take? How long do they take? They take big O of log n because that's the height. So if we can have that, then we get really nice efficiency. So the whole idea that we're going to be using is the concept of a self-balancing tree. So we're going to talk about self-balancing trees. So we're going to talk about self-balancing trees. In particular, we will consider a binary search tree called an AVL tree. Now, just for a little bit of perspective here, the AVL tree is something that's from about 1962. And if you're wondering what the A, V, and L stand for, it's really Adelson, Velsky, and the second name is Landis. So if you're wondering, this is one of the first proposed self-balancing trees, if not it is. There are more than just this self-balancing tree out there. There's such a thing called red-black trees, which have a very similar set of operations. So I'm going to be showing you the AVL tree for the next couple lectures at least. So I'm just going to, before we stop, I'm going to define one last thing. So a big part of the idea that we're going to use here, I'm going to define the notion of a height of a node. So I did something actually like this not too long ago when we were talking about heaps, and I said, oh, it sounds like a lot of jargon. We keep having to refer to levels and heights of subheaps or smaller heaps. This is going to give me the conception I need to talk about that. So the height of P is the height of the subtree rooted at P. The maximum depth of a subtree rooted at P. So we're going to use this idea of a height of a node in our data structure, where we're going to have each one of the nodes has some sort of height that's associated with it. And in the self-balancing tree, as we do insertions and removals, we're going to ensure we maintain that the tree remains height balanced. So next day we'll talk about how the big picture idea of how we're going to do that and some properties of so-called AVL trees. So I'll define next time what an AVL tree is. So I think this is the perfect place for me to stop. So thank you very much and have yourself a beautiful day.